Welcome. Today I'm going to look at the problems I've assigned in the Engel and Reid copy of Physical Chemistry for Chapter 3. I've assigned problems 1, 6, 9, 11, 16, 21, 27, and 35. So in just a second, we will start looking at those problems. Obtain the expression for isothermal compressibility of kappa equals -1 over volume dV dP at a constant T for a van der Waals gas. So we want to find and solve for dP constant T for a van der Waals gas. A van der Waals gas, remember, utilizes the equation P equals nRT over V minus NB, A N squared over V squared. Now this one is a little bit of a messy problem. Not overly hard, but a little bit of a messy problem. One of the key problems with the van der Waals gas is you can solve it for a in terms of pressure on the y-axis or temperature on the y-axis, but you cannot easily solve it for V on the y-axis. So what I'm going to do is I cannot solve this so easily, but I can solve, if I take the kappa equals -1 over V, I can solve this for 1 over dP dV. Now, what we have to do is we have to do the derivative of dP dV with respect to both terms to here. So the term dP dV, well, you're going to factor out all the constants and RT, and then we have to do the derivative of, so d over dV with respect to 1 over V minus NB. And factoring out all the constants, A N squared, you're doing the d over dV 1 over V squared. Okay, that in mind. This one is a little bit harder. You have to set up a UDU example where it's set that your U is equal to V minus NB. So that we're U D over DU times times the DU. So doing this, the result of this one is going to be, becomes negative nRT V minus N, all that is squared times 1, because du of V minus NB with respect to V is 1. Now this one becomes this one loses its negative and becomes positive 2 squared over V cubed. So all this is the result of our dP dV. and it's going to go into here. So right now we have this. We have kappa equals -1 over V times we'll switch around 2an squared over V cubed minus nRT over V minus NB squared. Okay, so we can factor those V's in if we can actually factor that V in. Doing that, it becomes, factor the negative in the V in, it becomes 1 over 2an squared V over V squared. Oh, actually, let's switch that around. It becomes positive nRTV for V minus NB squared minus 2an squared or V squared. Now, to make this one step prettier, we are going to flip this equation around. But in order to do that, we need to combine these two terms. To combine these two terms, we have to get them into the same denominator. So what I'm going to do, I'm going to multiply V minus NB squared on top, V minus NB squared on bottom. Side, I'm going to multiply V squared over V squared. So when we combine those together, we are looking at, so our kappa is now equal to 1 over nRTV cubed minus 2an squared V minus NB squared all over V squared V minus NB squared. Finally, last step, to put this up, over 1 over, it's the same at 1 over x is the same as x over 1. So kappa is equal to V squared V minus NB squared all over nRTV cubed minus 2an squared times V minus NB squared. That is what kappa equals to. So this is our proof for number 1. Problem number 6 reads as following. A vessel is filled completely with liquid water at 13.56 degrees C and a pressure of 1 bar. If the temperature of the system is raised to 82 degrees? 82 degrees C. The conditions are as follows. The beta of water, which is which is the expansion coefficient of water based on temperature, is 2.04 times 10 to the negative 4th Kelvin. And the beta of the vessel is 1.42 times 10 to the negative 4th. And the kappa of water, which is the isothermal compressibility of water, of our H2O2, is 4.59 times 10 to the negative fifth bars. So we're wondering essentially what is the pressure? Is the water will expand with the vessel, but it's going to expand, as we see here, more than the vessel. However, because the vessel is sealed tightly, it will be compressed instead. And so the pressure on the water will go up, shoot upwards. So in order to do this, we have to think about the volume, which is quite a little tricky. We don't know the initial volume of the vessel or the final volume of the vessel, but we do know one thing, that we can say the volume of the water is equal to the volume of the vessel, and that the vessel will expand with T, such that the VF of the vessel and of the water will equal the VI times 1 plus delta T. So the beta of the vessel, such that however much the vessel expanded with the temperature, it's going to be that plus a little bit more. So if the vessel is 10 is 10 liters, it'd be 10 plus 10 plus 10 beta temperature. If it's 20, it'd be 20 plus 20 times beta temperature. So we don't really need to know that. But, so we're looking at how does the pressure change with temperature and volume. Well, the change in pressure is equal to beta for the water. This is the pressure of the water. Beta kappa of the water, dt for the water, and the pressure dependence on volume is 1 over kappa volume dV. So integrating this for the temperature is simple enough, but integrating this for the volume is a little bit trickier. But so we now know a statement for, so integrating that becomes beta over kappa delta T, where we go from our temperature in Kelvin. So our temperature in Kelvin, 13.56 plus 273.15 becomes 286.71. And our other temperature, 82.0 degrees, we add 273.15 becomes 355.15. So we're just integrating straightforward. This part, the minus 1 over kappa, when we integrate 1 over v dv, it goes to negative 1 over kappa ln vf over vi. What we just said, vf over vi would be vi 1 plus beta delta t. Vf is that, and so vi is just vi. So what does that mean? That means, so you can look at natural log of 1 plus the beta of the vessel times the change in temperature. So let's look at this. First, quick, what is 1 plus beta temperature? 1 plus beta delta T is 1 plus 1.42 times 10 to the negative fourth. than the difference between 355.15 and 286.71, which that difference is 68.44. So 68.44 times 1.42 times 10 root negative 4. So really, the 1 plus beta temperature is going to be 1.0097. Use all of it for right now. All for right now. So let's look. We have that. We can take the net. So plugging all this, we have beta for the water, 2.04 times 10 to the negative fourth. And for the kappa for the water, 4.59, 10 to the negative fifth. Times our change, which we already calculated as 68.44. Minus 1 over 4.59 times 10 to the negative fifth. Now 1.00971848. So let's determine our terms. 4 times 10 root negative fourth divided by 4.59 and 10 to the negative fifth times 68.44. So right now I have 304.17 repeating here. And let's see, natural log of 1.00971848 divided by a really small number, divided by 4.59, 10 to the negative fifth. So minus 210.709. So 304.7178 minus 210.709 means the pressure experienced by that water, or that pressure on the vessel, it becomes 93.469 bars of pressure. So hopefully that vessel can withstand that intense pressure, but if not, that is what we're looking at. Number 9. Number 9 is one of the few examples of the use of your Joule-Thomson coefficient. So the statement, because dH dP at a constant temperature is equal to negative C sub P mu JT. The change in enthalpy of a gas expanded at a constant temperature can be calculated. To do so, the functional dependence of mu JT on P must be known. Treating argon as a van der Waals gas, calculate change in enthalpy when 1 mole of argon is expanded. 1 mole is expanded from 325 bars to bar. 1.75 bars at a constant temperature of 375 Kelvin. Assume that mu JT is independent of pressure and that mu JT is actually equal to, so they give us this 2A over RT minus B, all that divided by C sub P sub M. And C sub P sub M is equal to 5R over 2. For argon, what value of delta H would be if the gas exhibited ideal gas behavior? So, with that in mind, we need to first look up our A and our B for argon. We cannot simply do this without this. So A and B of argon are as follows. A is 1.355, which is in decimeters hextupled bars per mole Kelvin, bars per mole squared. So it's simply liter squared bars per mole squared. And B for argon is 0.0320, which is decimeters cubed per mole, which is essentially liters per mole. Okay. Now, because of this, let's set that up. UJT is this. C sub P is that. Then we can set that D sub H is equal to negative C sub P mu JT dP. We're going to integrate this. Now, we're going to make things a little bit easier. So, because of the nature of this and this, we get that we're integrating 2A over RT minus B, and you get delta P. So, in all intents and purposes, you have a constant times a change in pressure. Change in pressure. Well, now 2 times 1.355 over R, which is 0.08314, T, which is 375, all minus our B, which is 0.0320. So if you're following your units carefully, this is going to give you liters per mole, and that's going to be liters per mole, and our pressure going to be from 1.75 minus 3.37 from 325. You're going to give in bars. So we'll have to do a little conversion before we get this into joules. So let's start by solving inside this constant zone. Inside the first parentheses, we have 0.054921658. And over here, we have 1.75 times 1 minus 325, negative 323.25. When I multiply these together, I get negative 17.75 bar liters. So, and there in 1 bar liter, there is 100 joules. So 1775, negative 1775 joules per mole. Now, we can do for pretty much for an ideal gas, it's always going to be 0. Though we could physically prove it. We can prove this for an ideal gas. This is going to be 0. That H is that H is equal to U plus PV. And looking at, so what DH is equal to DU plus PdV and VdP. exchanging our partially differentiating this and exchanging what we know, we have C sub P dt plus dH dP dP. And we have C sub V dt plus du dV dV. And of course our PdV and VdP. Now, knowing that getting all of our dVs to one side, well, actually, no, I can exchange, getting the dTs to one side, you can get that this term goes to NR. C sub P minus C sub V is equal to NR dt. So C sub P, so your NR dt plus dH dP. But of course, under this situation where we say the temperature is constant, all that goes to 0. D sub T is 0. I can say that I can pull the dVs together. So du over dV plus P dV dP. And dividing both sides by dP, what we get is our d sub H over d sub P, constant T, is equal to d sub U, d sub V at a constant T plus P times dV dP at a constant T plus our volume. Now, lastly, we can exchange du dV for our known value. Our du dV is equal to T dP dt, a constant V, minus P. And we've now have a plus P. dV dP plus V. Now, canceling that out and using our dear friend, the cyclic rule, I think, let's see. Oh, actually, no. Just doing the move. So what is P dt? P dt is going to be NR over V. And dV dP is going to be negative nRT over P squared. So exchanging those two in there, our dH over dP, the constant T, is equal to T times nR over V times negative nRT over P squared plus V. So nRT is equal to P. Cancels 1. Negative, so nRT over P to the first, nRT to the first is exchanged for V. So this becomes negative V plus a positive V, which equals to 0. So mathematically, you can prove it to be 0, even though we should have already expect it to be 0 based on the fact it's an ideal gas. Number 11, a little bit easier one, a little bit simpler one. A 75-gram gold sample. A gold sample is at 650 degrees Kelvin, is dropped into a 180-gram sample of water at 310 Kelvin. In an insulated piece, a container can 1 bar pressure. Calculate the temperature of the system once equilibrium has been reached. Assume the C sub P sub M gold and the C sub P sub M of water is constant at their values for 298. So what they're saying is we're going to look up the C sub P sub M of gold and water and assume it's the simpler version, the constant version, rather than the complicated version. So for gold, we're going to just use 25.4 and save ourselves a little bit of 5.4 for gold. And for water, we're going to just say, oh, okay, water. Water liquid, we're going to just say that number is 75.3. This is actually as close to a Gen Chem problem as you will likely to get. Basically, what you have is Q of the gold is going to be equal to negative Q of the water. Q of the gold is going to be moles of gold times C sub P sub M of gold times delta T with negative moles of water, C sub P sub M of water, delta T of water. So first things first, we need to find moles of gold. Moles of gold would be our 75 grams divided by, that in fact is 196.97 grams in 1 mole, giving us say 0.38077 moles. The moles of water, we have 180 grams. We're going to just make a little assumption. We got 18 grams in 1 mole. We're going to equals 10 moles. So with that in mind, set this up. We have 0.38077 times 25.4 times, we're going to say TF minus 650 is equal to negative 10 moles times 75.3 joules per mole Kelvin times TF minus 310. And now it's just a matter of evaluating. 3877 times 25.4. So we get 9.671558 TF minus 6286.5127. This side, we have negative 753 TF plus 233,430. So we're going to get all the TFs to one side and all the non-TFs to the other side. So 233,430 plus 6286.5127 becomes, on one side, 239,716.5127. And 753 plus 9.671558 going to give us 762.671558 TF. Now the next step is then just isolating the TF. TF is equal to, so we take our value divided by 762.671558. You get our final temperature is 314.3 Kelvin. So yes, it didn't jump up by much. It didn't jump up by much, like 4 degrees. But you got to remember, we have a ton of water compared to gold. Gold is much heavier than water, and the heat capacity of gold is much smaller than water. So all that contributes to making the very low temperature change. Looking at problem 16 real quick. Problem 16. 16 is the Joule coefficient is defined by dt dv at a constant u is equal to 1 over c sub v p minus t dp dt at a constant volume. Calculate the Joule coefficient for an ideal gas and for a van der Waals gas. So, ideal gas, real quick, dp over dt is equal to nr over v for a ideal gas. Plugging that in, you get nRT p minus nRT over v. Well, what is nRT over v? But that is p. P minus p is 0. 0 times 1 over c sub v is 0. Any number times 0 is itself 0 for ideal. But d sub p dt for a non-ideal gas becomes nr over, over v minus nb. And now here's where it doesn't, because the a n squared over v squared terms drops out. So now, when I subtract this, we have 1 over c sub v. Well, p is no longer nRT over you get when we replace p, this becomes nRT over v minus nb minus an squared over v squared minus our nRT v minus nb. So you notice one thing drops out, but the other thing does not. This is going to drop out. So what we get is that is equal to negative an squared over v squared cv. So you get a value. You get a value that you can solve for. 21 is, starting from the van der Waals equation of state, find an expression for the total differential of dp in terms of dv and dt. So we're finding dp terms of you're finding dP is equal to dP dV, and dP dt for van der Waals. Now, let's see. By calculating the mixed partial differentials, determine if dP is an exact differential. So when you say dP dV and then do the dt, and then dP dt doing the dV, is this would this be a state? Would the van der Waals equation be a state function? Is dP over dV d over dt, is that going to be equal to d over dV dP dt? Is this truly a state function? So, okay. So the first thing we want to do is find out our simple partial differentials. So dV, dP dV, we've already kind of done this one, is equal to negative nRT V minus NB squared. If you don't remember, plus 2AN squared over V cubed. If you don't remember this one, go back to problem number 1. Problem number 1, we did that proof. We did that solution. Then dP dt is equal to just nR over V minus NB. So our partial differential is dP equals negative nRT over V minus NB squared plus 2AN squared V cubed dV plus our nR over V minus NB dt. But okay, so that's really the solution to that. But prove that this is a state function. So if I take this, and I do the d over dt to this. This part is going to drop out, and this goes to negative nR over V minus NB squared. If I do this, d over dV to this term, this is just going to be negative nR over V minus NB squared. So the question, is this a state function? Well, we get these same values whether we do the dP dV first or the dP dt first. Gives you the same value. So yes, the van der Waals equation state still gives you a state function value and fits the state function definition. Okay. 27 reads as follows. Because V is a state function, d over dP times dV over dt will equal d over dt dV over dP. Using this relationship, show that the isothermal compressibility and the isobaric expansion coefficients are related by the following relation. So d beta dP at a constant temperature is equal to negative d kappa dt at a constant pressure. Show this relationship. Okay. To do this relationship, we got to remember, what is our beta value? Beta is equal to 1 over V dV dt. And kappa is equal to negative 1 over v dv dp. So real quick, right there, from here, if I want to exchange this for this, this is going to be d over dp beta volume. And this, once again, is going to be d over dt negative kappa volume. So because they're both in terms of volume, we can divide out the volume. And so it literally becomes, if I divide both sides by volume, you get really only d beta over dt of dp, sorry, equals negative d kappa dt, which is really not that bad as far as all that goes. You just have to remember your expressions for beta and kappa. Number 35. Derive the equation that dH dt at a constant v is equal to c sub v plus v beta over kappa from basic equations and definitions. So, start things off. We need d sub h. So our basic starting equation is d sub h equals d sub u plus pdv and vdp. Doing the partial differential of the dh and du, we get that dh dt times dt plus dh dp, constant p, changing p, equals du dt and du dv plus my pdv and vdp. So all that's well and good. Now, because we have artificially set this as constant volume, any terms with dv are immediately x'd out. They're immediately gone because anytime you have a dv, that has to be 0. Now, we are going to make a handy exchange before we go any further. We are going to make the exchange that du dt is equal to cv, c sub v. So we have c sub v dt. And I'm going to go ahead and get the dh dp to the other side. Plus v dp and dh dp dp. Okay. With that in mind, I'm going to divide both sides by dt. Divide both sides by dt to get this stuff. So what I get d sub h dt, which is starting on the right track, is equal to c sub v plus v dp dt, the constant volume, and minus dh dp dt, constant volume. Well, here's where we get our conversion. If beta is equal to, beta volume is equal to dV dt, and negative kappa volume is equal to dV dP, we can use the cyclic rule to exchange dP dt for something else. Cyclic rule says dV dt dt dP dP dV equals -1. Well, we can say that dP dt equals negative dP dV dV dt. Once again, so that means that is beta volume. And once again, one quick thing, so that means that's -1 over kappa volume. So volumes cancel out, the negatives cancel out. So PDT is equal to beta over kappa. Plugging that in, beta over kappa, beta over kappa. And the last thing is how do we get rid of the DHDP? Well, DHDP is going to be equal to T dP dt is dV dP plus V, which is essentially for an ideal gas that is 0. Or our enthalpy essentially becomes 0 for an ideal gas. So what does that mean? That I can plug in this there, and so really all we have is CV plus V beta over kappa. And that's what we got. So now that's the end of chapter 3 homework. A lot of proofs, but they come up useful for practicing later. Understand? Okay. See you around.